Welcome everyone to our video on representing ionic and covalent bonds. And in this video, we are going to compare and contrast ionic and covalent bonding. And our focus is going to be how to use Lewis diagrams to represent the formation of both ionic and covalent bonds. So let's start off by looking at ionic bonding. So an ionic compound is some sort of regular arrangement, which is often referred to as a lattice of charged particles. And charged particles in chemistry that we're interested in right now are ions that are held together by an electrostatic force of attraction. Now think back to an earlier science course where you learned about static electricity. And so the electrostatic force of attraction is just the force of attraction which holds together, attracts oppositely charged particles. So positively charged ion and a negatively charged ion. And ionic bonds, now they can form in various ways. And so we'll see a different way of thinking about ionic bonds forming when we get into our solutions unit. But for right now, we'll just kind of think in general, ionic bonds forming in the process of a chemical reaction. And during that chemical reaction, valence electrons are transferred from the less electronegative atom to the more electronegative atom. And as a result, we end up with two oppositely charged ions, and those are held together by that electrostatic force of attraction. Now, you'll see already that I've used two different terms which are not exactly the same thing, ionic bonds and ionic compounds. So let's compare those first. When we say use the term ionic bond, that is referring specifically to that electrostatic attraction between oppositely charged ions. Positive ion, negative ion, attracted to each other. Whereas an ionic compound are many, many, many ionic bonds that, when put together, are found in a fixed whole number ratio. So that's part of our exercise today, is going to be to look at how to figure out that whole number ratio and why it occurs. So what we'll use for an example here is the bonding between calcium and fluorine. And so calcium, a metal, has an electronegativity of 1.0. Fluorine's electronegativity is 4.0. And if we subtract those two, we get a difference in electronegativity of 3. So we know that's going to be ionic bonding. Now, generally, if we have a group 1 or 2 element and a halogen, that's going to be ionic bonding, but it's always good to double check before you start this process. Our first step here is going to be to draw starting in 3, 2. Our first step here is going to be to draw the Lewis dot diagrams for each of these atoms. So calcium, group 2, 2 valence electrons. Fluorine, group 17, a halogen, 7 valence electrons. And remember how we draw these, that we put them in pairs on the 4 sides in a certain order. So ionic bonding is going to be a transfer of electrons from the less electronegative element to the more electronegative element. And we'll represent that with an arrow passing an electron from calcium to fluorine. Now, part of this exercise is to determine the ratio in which these compounds will bond. So the process we'll undergo is just going one electron by one electron, and we will stop when all of the atoms that we've drawn have either lost their outer shell of electrons or have completed their outer shell of electrons for that stable octet. Remember, that's what Lewis' theory of bonding is based upon. So here, calcium is transferred 1. Fluorine now will have 8. But now calcium still has another. So if you have leftover electrons on one atom, draw another atom of the other element. So in this case, fluorine. And now we'll transfer another one. And now we've reached to a point where both fluorines have completed their outer shells and calcium has lost its 2 valence electrons. Note that I use different symbols for these because that will enable us to represent this compound with Lewis dot diagrams. Calcium with a 2+ charge, and it's going to be a ratio. So 1 calcium and 2 fluorines, and each of these fluorines gained 1 electron, so they each have a 1- charge. And we'll draw them like so. And I'll just put a bracket around those fluorines saying that 2 applies to each of them. So 1 calcium, 1 2+ charge in a ratio with 2 1- charges. And note that here we have the charges balance, 2+ and 2-, net charge of 0. And that's an important concept, that an ionic compound is made up of charged particles. However, it is electrically neutral when we have the correct whole number ratio. So once again, this is not how we write a chemical symbol or chemical formula. This is how we will use Lewis diagrams to represent the formation of ionic bonds. So let's now take a look at representing covalent bonding with Lewis diagrams. So remember that covalent bonding occurs when we have 2 atoms which have fairly high electronegativities, but their electronegativities are fairly similar. So they both have strong pulls on the electrons, but neither one has a pull that's strong enough to take the bonding electrons away from the other. So as a result, they share those pairs of electrons, and that shared pair of electrons, which is holding those atoms together, that is the covalent bond. And when we are using Lewis structures to figure out how the covalent bonding might work between atoms, we have to remember what the ultimate goal here is, that covalent bonds will occur in ways so that atoms reach that stable noble gas configuration, S2P8, or that stable octet, as you would have called it in earlier grades. Because no electrons are being transferred, there's no ions being formed. And so when we have several atoms combining through covalent bonding to reach noble gas configurations, these combination of atoms are called molecules. One thing that you need to be able to do is to figure out the structure of a molecule using Lewis diagrams. So if you're given a molecular formula, can you take that formula and figure out what the shape and what the bonding arrangement is going to be for those atoms? There are a few steps that you're going to do, and we'll expand on these as we get to more complex molecules. So If you only have a molecule with two atoms, you're just going to place them beside each other and start figuring out the bonding. If you have more than two, what you're going to do is take the element that has the highest bonding capacity. And remember, bonding capacity refers to the number of bonds that an atom needs to make in order to reach that S2P6 configuration. So you're going to place that atom in the middle. And then you're going to form a single covalent bond between all of the outside atoms and the center atom. And that makes the molecule. So now you've connected all the atoms, and then you're going to check to make sure that each atom has an octet. And if they don't, then your final step is going to be adding double and triple bonds, if they're needed, to complete the octet of all atoms. So let's now take a look at a few examples of how we do this with covalently bonded molecules. Okay, so we're going to look at two examples here. Our first example will look at hydrogen chloride. So remember, if we're asking to use Lewis diagrams to show the bonding, first thing that you want to check is the electronegativity difference. And if you check that for hydrogen and chlorine, you'll see that it's going to form a polar bond. So our first step is to draw the Lewis dot diagrams for the two elements. Now, recall with the ionic bonding, we drew different symbols. Since we're just sharing the electrons here, we're just going to draw the dots for all of them. So the formula has one hydrogen and one chlorine, so that's what we're going to draw. And then we're going to take the unpaired electrons and draw a circle between them, and that represents the shared pair. And then we'll check to make sure all of the atoms have reached a noble gas configuration. So for chlorine, 1, 2, 3, 4, 5, 6, 7, 8. And then hydrogen, because it's in period 1, its noble gas configuration is going to be that of helium with 2 electrons. So 1, 2, and that is good for hydrogen. So we would have a stable molecule. Now, sometimes these circle and dots can get kind of unwieldy. And so another way we can draw Lewis diagrams is drawing a straight line to represent the shared pair of electrons. Okay, so here's another example, NH2Cl. So here we now have 1, 2, 3, 4 different atoms that are involved in this molecule. And so now we need to have a center atom and terminal or outer atoms. So we'll go through each atom here. Nitrogen has a bonding capacity of 3. I know that because it's 3 elements away from the noble gases. Hydrogen can form 1 bond, so it has a bonding capacity of 1. And chlorine is a halogen, and so it has a bonding capacity of 1 as well. So nitrogen has the highest bonding capacity. So I'm going to place that in the middle, and then I'm going to simply spread my other atoms out and then draw my dots for my Lewis dot diagrams. Nitrogen, 5 valence electrons, 2 in the s, 1 in each of the p orbitals. And then chlorine, as we saw from the other example, 7 electrons. And remember that our first step here is going to simply connect the atoms. So this makes the molecule. Well, that's a horrible circle. Okay, see what I mean by unwieldy, okay? So 1, 2, 3, 4, 5, 6, 7, 8. So nitrogen's got its octet. Chlorine, 1, 2, 3, 4, 5, 6, 7, 8. And then each hydrogen has 2. So we call this a valid molecule. You don't necessarily know whether it's the actual molecule which is going to form, but if you follow these steps, you'll usually get the right molecule. And once again, we can simplify this Lewis structure by just drawing straight lines to represent the shared pairs of electrons. So either of these structures are valid Lewis diagrams. I would get used to drawing these because this is the way, as you take further chemistry and biochemistry courses, that you'll see that they're drawn. So here, once again, the bonding pairs of electrons are represented by a straight line. That straight line represents two electrons that are shared, and all of the electrons that are, and you can see I made a mistake here already, so let's just go back here, and I'll just add in those dots, because that is the one thing that we need to see in all Lewis structures. So all valence electrons need to be shown. So bonding pairs as straight lines or as dots with loops, and then the lone pair electrons, the electrons that are not involved in bonding, are always shown as well.